Good morning, everybody. Here we are starting the last section in Organic 2, Test 4 on acids and their derivatives. We'll do acids and their derivatives first, and then amines, even though in our book amines comes first. So some acids are shown on this page. We have ethanoic acid. It's a 2-carbon acid. We have the butanoic acid. It has 4 carbons in the carboxylic acid. So we take the base name, drop the E, and add oic acid to name whatever we have. Okay. If we have 2 acids in it, it would be a diacid. So we have to put that prefix in for the oic acid in there. So what do we know about the structure and property of carboxylic acids? The carbon atom of the acid moiety is an sp2 hybridized atom, that carbon right there that I drew in blue. So its geometry is trigonal planar. We know all that from Org 1. Both oxygens have a couple of lone pairs on them, and that gives them the ability to hydrogen bond to another carboxylic acid. So we can have a lot of hydrogen bonding going on in there. Now, the acidity of the carboxylic acid, remember, the functional group is the carboxylic acid, so obviously it is an acid, so we can add a base, and the base can go pull a hydrogen off of the carboxylic acid to give us the carboxylate. We can draw resonance structures of the carboxylate where the lone pair on the oxygen with a negative charge goes down to form a double bond, and we break the double bond and we get the other resonance structure of the carboxylate. Okay. Carboxylic acids at physiological pH. Remember the Henderson-Hasselbalch equation. You'll never hear me say that again. You haven't heard me say that yet. We can use it to calculate buffered equations like the human bloodstream, which has a pH of about 7.3. Okay. When you get into biochem, you'll get a lot more of that. So substituent effects on the acidity of a carboxylic acid. A plain carboxylic acid, acetic acid, is roughly 4.8, 4.7, right around in there. So if we add a chlorine onto the alpha carbon of the carboxylic acid, we have that electron pull of the chlorine being such a high electronegativity that it lowers the pK from the high 4s to the high 2s. If we put 2 chlorines on there, it goes down to about 1.3, and if we put 3 chlorines on there, it goes down below 1. So it's all about having an electron withdrawing group on that alpha carbon, lowering the pKa of the carboxylic acid proton, making it more acidic, making the carboxylate much more stable. Now, we learned a long time ago, and I know on the last test we all forgot it, but we can take a triple bond, an alkyne, and we can ozonolize it, and we can ozonolize it to 2 carboxylic acids by, remember, ozone completely splits all 3 bonds apart, so we're breaking 3 carbon-carbon bonds. We got to form 3 bonds to oxygen in that. So we can cleave an alkyne to form a carboxylic acid. We can take an alcohol and we can oxidize it with sodium dichromate and sulfuric acid, and we get the carboxylic acid. Remember, PCC and swern we talked about on the last section, that only gives us aldehydes. It won't go all the way to the carboxylic acid, so be careful what you use in your oxidations. We can also oxidize alkyl benzenes as long as there is 1 hydrogen on the benzoic carbon. We can add sodium dichromate or concentrated KMNO4 and heat. And what we get out of either of those is it will oxidize that benzoic carbon all the way up to benzoic acid. Doesn't matter what else is off of that carbon, as long as there is 1 hydrogen on that, we can oxidize it up to the carboxylic acid. We can hydrolyze a nitrile Okay, we did it in the last section. We did aldehydes and ketones, did all of the different transformations with them. But here we have the nitrile. We have 3 bonds to a more electronegative atom. So if we add acidic water to, we can, cleave the triple bond and end up with 3 bonds to oxygen, and the functional group we know of with 3 bonds to oxygen is a carboxylic acid. So we can cleave that, and we'll draw that mechanism later in this section. Right now we're mostly just talking about the reactions. Okay, we can convert an alkyl halide into a carboxylic acid a couple of ways. One, we can add cyanide to it and do an SN2 to get the alkyl cyanide, and then that we can cleave with acidic water and a little bit of heat to form the carboxylic acid. Or we could turn the alkyl bromide into the Grignard by adding magnesium. The Grignard can then add CO2, and we extend the chain 1 carbon, and after adding acid to it, we would get the carboxylic acid on there. So the mechanism for this one is really short and easy. The Grignard carbon adds to the carbon of the CO2. When it adds to that carbon, CO2, one of the double bonds has to break. We form the carboxylate, and then to that carboxylate we add acidic water in the workup, and we protonate it and get the carboxylic acid. We can do this sort of thing to turn bromobenzene into benzoic acid, brominate it. We know how to brominate benzene, bromine and iron. So we could start with benzene, brominate it, make the Grignard, add CO2, and we can make benzoic acid. Okay, once we have benzoic acid, what can we do with it? We can add LAH to it and reduce it down to the benzyl alcohol, of which then the alcohol we could do lots of things too going along to change it into many different functional groups. So if we were to draw a mechanism for this, we could see that carboxylic acid, we know LAH has a very reactive H-. It's the most reactive of all. So the first equivalent of hydrogen off of LAH, we're going to remove the acid hydrogen off of the benzoic acid to make the benzoate. Then to this, we could have, well, wait a sec. It wants me to do it stepwise. So we'll form the carboxylate. On the next step, we take the carboxylate and we can add more aluminum hydride to it, and we can add 1 hydrogen on there to give us 2 O- and a hydrogen on there that can react with an ALH3, one of them attack to form a bond on there. So we would get a pH with an O-, an H, an O, and an ALH3. We can reform the carbonyl, kicking out that leaving group, and that gives us an aldehyde, of which the ALHHO- could transfer 1 hydride off of it to reduce it down to the alkoxide, where we've added 2 hydrogens on, and then we can just add acid to that in the workup to make the alcohol. So as you're drawing these mechanisms, make sure you remember the charges on things. Is it negative or is it positive? Because that really matters in what we're trying to do. Some of you are kind of lax with your charges. It happens every semester. be careful. You know, chlorine with 4 lone pairs on it has a negative charge, not a positive charge. So just be careful. Think about what you got as you're going along. We can also reduce a carboxylic acid down to an alcohol with borane. It only works with carboxylic acids. It doesn't work with ketones. So benzoic acid, we can make benzyl alcohol. But if we have the substituted acetophenone with the carboxylic acid off of it, we still have the substituted acetophenone. We've just reduced the functional group of the carboxylic acid down to the alcohol. So what kind of carboxylic acid derivatives are there? We know a carboxylic acid, benzoic acid. If we change the OH to a Cl, we have an acid halide, an acid chloride. So it is benzoyl chloride. So we dropped the ic acid and added oil chloride on there. Okay, we can go to an anhydride where we have all of this off of the carbonyl. This is benzoic anhydride. It is an acid anhydride, and anhydride is the loss of water. So we've lost an equivalent of water out of 2 carboxylic acids to get the anhydride. We have the methyl benzoate here, where we have an ester, the methyl benzoate. The methyl is the alkyl group off of the oxygen of the carboxylate. That's why it's a benzoate. Okay, the conjugate base of the carboxylic acid. It's an ester, and then we have the benzamide and amide, where we have the NH or NR, where it could NR2, where it could be carbons or hydrogens off of the nitrogen. It doesn't matter which. So carboxylic acid derivatives in nature. Esters and amides are widely found in nature. You'll see them a lot when you get into biochemistry. Okay, we'll talk about the reactivity as we're going along with these, but the naming an acid halide, as we said above, drop the ic acid and ended in ill halide. Okay, so benzoyl chloride, benzoyl bromide, things like that for what we have. If it's off a ring, it's changed to a carbonylic acid to a carbonyl chloride, so on and so forth. Naming acid anhydrides, you drop the ic acid and really just drop the acid and make it the anhydride. Sorry. Methyl benzoate, we turn it into drop the ic acid, add 8. So we're talking about the carboxylate of whatever acid we would have. So this one, the carboxylate this would be formed from, was benzoate, the carboxylate of benzoic acid. And what we have off of it is a methyl off of it, so methyl benzoate. Then we have the benzamide, drop the ic acid, oic acid, and add amide. And nitrile, benzonitrile, drop the ic acid and add onitrile or nitrile on there as you're going along. Okay, so those are the different functional groups you should know as we're going along. Now, if we think about the reactivity of them, the order of increasing reactivity is shown here, where the amide of the different acid derivatives, the amide is the least reactive, the acid chloride is the most reactive, and it all comes down to the leaving group. If we look at what leaves the carbonyl in each one, which of those is the best leaving group? Well, of course, the chloride, because the HCl is the strongest acid, so Cl minus is going to be the weakest base. The weakest base is the best leaving group. So the better the leaving group, the easier it is for the thing to leave off of the carboxylic carbonyl. So in this, the acid chloride is going to be the most reactive. It's going to be the one that's easiest to react to form something else. The carboxylic acid isn't on here because it's only reactive in an acid solution, whereas these can react in base, at least the top three, easily. So, a generic mechanism for this section. We have a leaving group on our carbonyl. We add a nucleophile to it. What can happen? Well, the nucleophile adds to the carbonyl, breaking the carbon-oxygen double bond. It is not an SN2. Do not draw an SN2. I'll take out 5 points. Don't go there. It adds to the carbonyl. We form the tetrahedral intermediate, and then once we have the tetrahedral intermediate, we can reform the carbonyl, kicking out the leaving group. So this is a nucleophilic addition and then the loss of a leaving group to get us to our product in this reaction. Okay, in almost every mechanism we draw, base catalyzed in this section will be nucleophilic addition, where we break the carbon-oxygen double bond, forming the tetrahedral intermediate, and then reform the carbonyl, kicking out the leaving group.